Okay, so moving on to the next example, we have NH2OH. Now, with this particular molecule, some of them you really don't even need to draw the Lewis structure. Some of them you can look at and identify whether or not the molecule is going to be polar or not. And what you can see here is that when we have nitrogen as our central atom, we're going to have two hydrogens bound and also an OH group. So even without drawing the complete Lewis structure here, what you can see is that we have our central atom and you have two hydrogens bound and you have an OH group bound. So what this means automatically is that this is a polar molecule. So looking at this, because this falls into the category of where we have a different atom bonded to the central atom, so you know there is a net dipole moment, so thus the polar molecule. Now since this is a polar molecule, you know that you're going to have London dispersion forces present, and you're going to have dipole-dipole forces present. But you also have to ask yourself, do I have a hydrogen bound to an oxygen, nitrogen, or fluorine? And what you see is that you have a hydrogen bound to an oxygen within this molecule. So that means you also have hydrogen dipole-dipole forces present. And when comparing these three, and we talked about them in terms of their relative strength, you know that the hydrogen dipole-dipole force is the strongest. Now, if we move on to example number 4, we see HBr. If we very quickly draw the Lewis structure for this molecule, we see that we have HBr. And if you look at this molecule, clearly you can see that it is definitely a polar molecule. It has a net dipole moment, it has polar bonds, and you can see that we generate this partial positive and partial negative. So it has polar bonds, it has a net dipole moment, therefore it is a polar molecule. Therefore we know there's going to be London dispersion forces present and dipole-dipole forces present. We have to ask ourselves, is there a hydrogen bound to an oxygen, nitrogen, or fluorine? And within this particular structure, there is not. So we do not have hydrogen dipole-dipole forces present. So what that means in terms of strength is that the dipole-dipole force is the strongest. Now, looking at the next example, we have H2. So if we draw the Lewis structure very quickly, we see that this is the Lewis structure for H2. And what we see is that the difference in electronegativity for this molecule is equal to 0. Therefore, we know that this is a non-polar bond, which means that this is a non-polar molecule. So since this is a non-polar molecule, we know that the intermolecular force present is London dispersion forces, and since this is the only intermolecular force present, we know that it has to be the strongest. If we move on to example number 6, we see that we have this structure here, CH3OH, and this is actually what's known as methanol. This is its common name. And with methanol, if we look at the structure, we have a carbon with 3 hydrogens bound, and it has an OH group attached as well. Now, clearly you can see that you have polar bonds because carbon and hydrogen and carbon and oxygen and hydrogen do not have the same electronegativity, so you know that you have polar bonds. And then you look, which means you can either have polar molecule or nonpolar. So you have to ask, do you have a net dipole moment? So do you have a lone pair bonded to the central atom? And we look at the carbon and we see, no, carbon is our central atom, there's no lone pair there. But do we have a different atom bonded to the central atom? We see that, oh yeah, we have 3 hydrogens and 1 oxygen. So that is a yes, which means that this is a polar molecule. So since we have we have polar molecule, we know that the intermolecular forces present are London dispersion forces and dipole-dipole forces. So we have to ask ourselves the last question. Do we have a hydrogen dipole-dipole force interaction? And what you see is that we have a lot of hydrogens, but they're bonded to a carbon. Those are not hydrogen dipole-dipole forces. This hydrogen, however, is bonded to an oxygen, which means that we do indeed have hydrogen dipole-dipole force present. And we know that this is the strongest intermolecular force present out of the three. If we move on to question number 7, we see IBr. If we draw the Lewis structure for IBr, we know that this is definitely a polar bond, and therefore we know that I and Br do not have the same electronegativity, so the difference in electronegativity is not equal to 0. Therefore, we know that we have a polar molecule. And since we have a polar molecule, we know we have London dispersion forces present, dipole-dipole forces present. We have to check, do we have any hydrogens bound to an oxygen, nitrogen, or fluorine? And with this one, we do not. So these two are the only intermolecular forces present, and we know that the dipole-dipole force is the strongest. All right, if we move on to the next example, we have carbon H2F2. So if we draw this structure, we see that in looking at this molecule, we have polar bonds because carbon and hydrogen and carbon and fluorine do not have the same electronegativity. Then we have to ask, do we have a polar molecule or a nonpolar molecule? And we look at the carbon and we know that we have 2 fluorines and 2 hydrogens bound. But we can kind of draw them so that they cancel themselves out in the Lewis structure, if you will. But remember, the third thing that we have to ask ourselves about polarity is the 3D shape. And since this has 4 regions of electron density around the carbon, we know that it has a tetrahedral geometry. So we know that all 4 of these are equivalent. We know that they do not cancel each other out, even though in this structure it kind of looks like they do. So because that occurs, there is a net dipole moment. We know we have a polar molecule. So now that we know we have a polar molecule, we know what intermolecular forces are present. We have London dispersion forces. We have dipole-dipole forces. We have to check, do we have a hydrogen dipole-dipole force? And what you see is that we do not have any hydrogens bound directly to a fluorine, oxygen, or nitrogen. So therefore, there is no hydrogen dipole-dipole force present. Therefore, this dipole-dipole force is the strongest.